Now, one thing about thermodynamics, however, is that it's not necessarily concerned about the detailed mechanisms of heat transfer, nor is it always that concerned about things like pressure drops and lines. Thermodynamics is more of a macroscopic approach to energy system analysis. That doesn't mean that those other areas are not important. They're critically important for doing the design of this. However, for examining the performance, thermodynamics does not necessarily worry about those areas. That would be left to other subsequent design. So if you look at a thermodynamics textbook, you'll quite often see heat transfer just as capital Q, and it doesn't get into details in terms of how that heat transfer is achieved. The type of heat exchanger used would be irrelevant. We just need to transfer a certain amount of heat. In a line, there may be pressure drop that is displayed. However, we would not be looking at the details about that pressure drop. We would just know that there's a pressure drop in the line. So in thermodynamics, what we do is quite often we will model the system as being ideal. So that is no losses. And then what we do is we assign efficiencies to the different components that we might have within our cycle. So for example, a pump, you put in a certain amount of work, but all of that work does not go into the fluid. Some of it would be lost to heat generation, for example, attributed to turbulence that might be within the pump. They're the same with an expander. You may have separation on the blades, and that would lead to inefficiencies and losses. And what we do is we quantify those losses through the component efficiency, and that's something that we'll be looking at in this course. So what we're going to do now, let's take a look at how thermodynamics may view the fireplace we've been talking about. So thermodynamics would model the fireplace as we quite often use two different diagrams in thermodynamics. We have one which is called the process schematic. So I'll write it over here on the left. And the other schematic we have is called the process diagram. So first of all, let's take a look at the cycle that we just looked at and draw out the process schematic. So recall what we had a pump. And with the pump, we're going to be doing work, but in this case we're doing work on the fluid, so it's what we call work in. The fluid comes along, and in this schematic, I'll draw it in this manner. And on the schematic, what you'll see are little arrows indicating the direction of flow of the fluid. Another thing that we will do on the schematic is we put horizontal bars and then a number beside those bars. And that indicates the state of the fluid. So here you can see as we go across the pump, the pressure is rising and perhaps the temperature rises a little as well. But we're going from state 1 up to state 2. And then what we do, we go into our boiler, and that boiler in our case was actually the fireplace. And in the boiler, a process is taking place, and that is a process of heat addition. So we have Q in. We then come out of the boiler, and I'll draw my little arrow. I'll put a hash so that we know that that's state 3. The working fluid comes out of the boiler, and then it flows into our expander. And what does an expander do? It generates work. So we have work out. And then the fluid comes out of there. It's at a new state that I'll call state 4. And it then flows into a device that we'll call the condenser. And so this was the turbine. And what the condenser does, it rejects heat to the surrounding. And the reason is because the remaining vapor coming out of the turbine has to be converted back to a liquid prior to it coming all the way back here to where the pump is. So I'll draw an arrow showing the flow. So that would be what a process schematic would look like for our fireplace. Now the process diagram, there are different ways that you can look at the states within a thermodynamic cycle, but one of the most popular ones would be the TS diagram. And so here I'll put temperature on the vertical. S is entropy, and that is on the horizontal axis. Now let's see our working fluid is water. It could be other ones, but I'll draw the TS diagram for a working fluid of water. That's what the TS diagram would look like. And the things to the left here denote compressed fluid. Over to the right would be superheated fluid. And then in the middle here, that's the two-phase region. So we start off in our pump, and we have a liquid, and that is at state 1. And then what happens is we go into the pump and we're pressurizing the liquid, and we go up to another state, that's state 2. And so what I'm doing is I'm drawing constant pressure lines on the TS diagram here. So this one may be 3 megapascals. I apologize, that's hard to read the 3. Let me clean that up. So this could be 3 megapascals, and then this one here may be 100 kPa. So atmospheric pressure. So I'm going to draw arrows just to show the direction that we're going in. And then what we're going to do, after we go through the pump and then into the boiler, we get up to a point here that I'll call state 3. So that would correspond to where we are after the boiler in our process schematic. And then we go into the turbine. And in the turbine, the temperature is fixed. And remember, we said we would assume that it's ideal, and therefore the entropy is not changing. And that brings us down then to state 4. And then we come back across the condenser and we end at state 1. So that is a way that we would represent our more efficient fireplace using thermodynamics. And so this gives an example of the types of things that we'll be doing in this course. And the tools that we'll be exploring. We're exploring tools that enable us to figure out whether an idea may be feasible or efficient. And we are always dealing with energy transformation. So energy going from, in this particular case, from logs or a fuel, chemical energy, and then being transformed into thermal energy. And if all works well, then what we do is we transform that thermal energy into mechanical energy in the form of work. So if we look on our diagram, we have work. Heat in, that is through our fuel. And then heat out, that becomes thermal energy that we can use for some other purpose. And consequently, that is how we could build a more efficient fireplace. Thank you very much.